Hi, folks. This is Sridhar Ramakrishnan, and welcome to our webinar this month. Before we get started, a few quick bookkeeping items. The presentation by Lacky will begin shortly and go until approximately 1 p.m. Lacky has a prior meeting scheduled immediately thereafter, but he might stay for a few minutes in the event that people have additional questions or want to talk. The slides and the recording will be available at the end of this presentation. Please log into your Malibu account to view them. Please keep your telephone or microphone muted at all times. Only unmute yourself to ask questions. And if you've dialed into the conference by phone, you must enter your audio PIN. I can only unmute you if you do so. And for those of you who prefer to ask questions by instant message or because you find yourself muted, please ask your question there. And Lacky has indicated that he welcomes questions throughout the webinar. So please ask them, and hopefully you get it. Okay. Let's see. I guess let's get started. Before that, one point of information for all of you. A little bit of bragging, I guess. About a month ago, a few of us from Malibu, 3 of us, entered the FTC National Civic Day of Hacking. The idea was we all get these telephone calls at night when we're about to sit at dinner. So there's this challenge that the FTC organized to try to see if you could come up with better algorithms for figuring out what are spam calls. And so they actually have a set of calls that have been designated spam, and then there was a set that we were required to sort of algorithmically determine whether they were spam or not. So anyway, 3 of us entered that contest, and we placed second. There'll be an official announcement of that in the month of August. So thanks to Shuping and Arjun for participating. It was fun, and hopefully there'll be a little bit more of these contests that we enter. So anyway, I guess with that, let's go ahead and get started with Lacky's presentation. Lacky is here today to talk to us about latest GPU technologies and applications. Lacky is a Senior Director of GPU Architecture at Nvidia, where he's been driving new GPU technologies for the last 11 years. Prior to Nvidia, he's had various architecture and performance-related positions at Transmeta and at HP. I have had the privilege of knowing Lacky and working with him for almost 20 years now from HP, and he and I co-founded OmniShift, which was our first startup about now, I guess, 15 years ago. Lacky received his bachelor's in computer science from IIT Mumbai and his master's in computer science from University of California, Berkeley. Lacky, with that, can you go ahead, please?
Sure. Thanks a lot for the introduction, Sridhar. And so, let me go ahead with the presentation here. Can folks see?
Yeah, you can see your slides, Lacky.
Okay, cool. So a lot of people are typically, in my experience, are pretty familiar with CPU. You learn a lot about it in the computer architecture class. At school. A lot of folks are familiar with what are GPUs. You ask somebody, I asked my son what's a GPU, and he's like, what the heck are you talking about? So I'm here mostly to talk about what a GPU is, talk about what people use it for, a little bit about what is internally inside the GPU, how it's different, what are some of the applications, some of the challenges, and then we'll answer questions and also talk a little bit about as a teaser, a brand new technology that Nvidia is coming out with. It's called NVLink, and I'll walk through that as well. Okay. Again, as Sridhar mentioned, feel free to stop me at any time with any questions or anything you have. Going to mostly be talking about about the GPU from the Nvidia perspective, since I've worked with Nvidia. The Nvidia GPU is basically used as, if you will, in basically 3 main areas, right? So on the PC side, a lot of people use basically the GPUs to do a lot of gaming. If any of you are gamers, most people prefer using Nvidia GPUs to play games because at the end of the day they can play the games with basically the maximal settings that you can possibly get. A lot of the people use also the GPUs to basically do a lot of design work. A lot of CAD tools, a lot of basically workstations use the GPUs people have started using more and more GPUs into basically in the enterprise side to do virtualization. So you have your server in the enterprise, and you basically have a lot of desktops, which basically are essentially streamed, if you will, from the server. So you can basically serve high-end applications by having them run just on the server.
A quick question here.
Sure.
Somewhat basic, but what is the definition of a GPU? What does GPU stand for?
Sure. The GPU stands for graphics processing unit instead of the CPU, which is the central processing unit. So, sorry, I should have started there. So yeah, that the enterprise virtualization piece. A lot of people have also started using the GPUs for high-performance computing stuff. So in addition to basically being good at graphics, GPUs have a lot of math inside them, which I'll walk through in a bit. And so people have figured out novel ways of using this math that is inside the GPU to do various high-performance computing workloads. And I'll go through some of the examples there. And then more and more people are also using GPUs on the mobile side. So when I mean by mobile, this is basically some of it cell phones, tablets, but also the mobile side, basically also in the cars. The car is basically becoming essentially a computer on wheels, and you will see how people use GPUs in the cars as well. So with that, let me sort of go inside basically, what is inside the GPU. So I'm going to be talking mostly about the Maxwell GPU. This is the most advanced GPU that we have just recently launched, and it has basically a lot of new functionality and features, and it's basically, the CPUs may have stopped fully following Moore's law, which is 2x performance over previous generations. But the GPUs have continued to still follow Moore's law over the last few years.
Lacky, a question?
Sure.
The questioner says, why do you say HPC and cloud service providers in mobile? Isn't the GPU on the device, that is the phone?
Okay, so the question, as I understood, is where you say GPU on the cloud service provider and mobile. So in the cloud service provider, the GPU is actually in the cloud. It is sitting essentially in the servers. Right? We have GPU sitting in the server farms. Like in the Amazon, you can go to AWS and you can actually rent out GPUs to run stuff. Is that the question? Do you understand that?
Yeah, I think so. I think, Sundar, if you want to follow up, you can ask that or send me a follow-on chat. Okay, so let's see. Lacky, go on, please.
Sure. Okay. So one of the things that we do really well with the GPU, and basically this is where we have sort of traditionally been extremely good at, but is basically provide innovative stuff so that you get more and more realistic images. And the GPU is extremely good, essentially, as doing graphics. And so every generation, we add new features that basically brings in photorealism in games. So if you basically go to movies and stuff, you will see a lot of photorealistic stuff that is done by by processing. But that doesn't have to be real time, right? What we need to do in the GPUs is make sure that we also deliver something that is real time. And so a lot of innovative features that goes into the GPUs to make sure you get real time photorealistic images. And so the most critical thing to make the stuff look real is lighting, right? That's the thing that is extremely hard to make it look real. People can basically take pictures, draw images and stuff, but to get lighting to happen such that it looks real, that is the biggest challenge that people have. And so that's why we keep basically innovating and stuff to to add features to make lighting become more and more real. So I'll walk through some of the examples and stuff there. I also want to basically make sure when I say a Maxwell GPU, people understand that there's not is one product that we actually sell. The great thing about GPUs, and it's also sort of somewhat different from the CPU that the CPUs are getting there, is we can scale from a really, really tiny chip to a massive chip that basically, a single chip that goes onto the cloud. So the chip that is basically built, the GTX 980, which I basically show, it has basically about 5 billion transistors in it, right? So it is a, it's something that basically it's one of the biggest chips that we build. Other than FPGAs and GPUs, you won't see a single chip that is built as big. Okay. So the GPU, so differences from the CPU, right? We are extremely good at basically doing processing of images and stuff. We are extremely good at scaling, so we can build something from the low end to the very high end. And I'll give you an example of a picture that you can basically see here. This, we basically think of doing this basically in real time, where you can essentially see lighting, where you can see essentially some smoky-like stuff in the background. You can see a lot of lighting, a lot of shadows, basically, in the foreground, at the back of the neck and stuff. You can, if you actually play this game, you'll see the shadow of the kite and this boy following the kite. You can see all this perspective. As you go closer, you'll see all the details of all the trees and stuff. Doing all of this thing at basically real time takes a massive amount of processing throughput, which is all essentially packed into the GPU. So the differences between a CPU and a GPU is essentially, I would say, at a high level, there are three main things. One is we have way more processing throughput. Second is we have way higher memory bandwidth. And the third is we have basically some very special fixed function hardware in the GPU, which basically helps do graphics processing way better than any other processor. And so I'm going to use this picture actually and spend some time on here to explain, a little bit about what I'm talking about. So as I talked about that GPU, if you look at this, it's basically about 5 billion transistors in this. The yellow parts, if people can see my cursor. Can anybody see the cursor?
Yes, Lacky, we can.
Okay. So the yellow part, these are very special units basically in the GPU, which are extremely good at basically processing triangles and points and lines, and basically mapping basically objects, breaking them up into triangles, and mapping them to pixels on the screen. Okay, you call them, you can see, you call them raster engines. So the scene as a specified is always specified in terms of basically objects and triangles, and we have to map where those triangles fall onto the screen. Okay.
Lacky, a quick question.
Sure.
That previous screen, where you showed the image of the boy with a kite, that is a synthetic image that is being generated by your chip, right?
That's correct. That's a synthetic image. That is not a picture. That is a synthetic image that is generated in real time. That means that basically more than 30 frames per second on the chip.
Okay, yeah. So I think I just wanted to bring that out because otherwise people might assume it's a photo being somehow enhanced. But this is actually sort of generating, what might be completely realistic images that can be used in games and so on and so forth, right?
Yep. Okay. So the scene, like the one that in the previous picture, is essentially specified in terms of objects and triangles and stuff, and that essentially gets mapped into where on the screen that thing falls. there are these yellow fixed function units, as we call them, that basically is the secret sauce in the GPUs that basically does this functionality at ridiculously high throughputs. The green stuff is basically, those are the math engines. Just like if you're familiar with the CPU, there is basically an ALU on the CPU. So those are essentially all of our ALUs, if you will. We call them CUDA cores. CUDA is essentially a special programming language that people use to program the GPUs on, and so it's a lot easier for us to explain to people in terms of CUDA, which is essentially C like programming. And so I'll give you an example about what CUDA is in a second. But so all the green stuff is essentially the math or the ALUs. And then all the light blue and gray stuff is essentially all the memory system. And so most CPUs basically talk to DDR2 or DDR3 memories, have a certain amount of bandwidth. The GPUs basically have special memories that they talk to, and which basically have a substantially higher 5 to 10x times higher bandwidth than typical CPUs do. And so all the blue and gray portions is basically essentially all the logic on the GPU's die that basically provides this high bandwidth so that we can fetch data really fast from memory, feed it into the green ALUs to process stuff, and use basically the yellow fixed function units to essentially translate it into basically pixels that come out on the screen. Okay, does that make sense? Anybody have any questions before I go forward?
I think we're okay, Lacky.
Okay. Okay, so let me jump a little bit into what is CUDA, right? And what does CUDA actually provide? So CUDA is basically, a few years ago, Nvidia invented this GPU computing or CUDA architecture. So with this architecture, every SM is basically our ALU. It's called, it stands for shader multiprocessor or streaming multiprocessor. Different people use different terms, but that's what the SM stands for. And so this picture out here is basically is one SM, which has internally basically a lot of math units. And so each SM has a small amount of high-speed on-chip memory that can be used to share data between different threads. So every one of these things that you see as SP is running a separate thread. Right? So you get an instruction, you take the same instruction, and you run across all of these SPs. This is basically the shader processor. Okay, and all of these shader processors use the shared memory to basically communicate across each other. And then they basically, the thing that's this texture is basically a version of the load store unit that's there on the CPUs. On the GPU, we basically call it a texture, because what a texture essentially does, in addition to fetching stuff from memory, like a particular picture, it will also filter it. It has all kinds of filtering functions in it, so it does basically loads and stores along with filtering. So that's why we call it the texture.
So Lacky, a quick question.
Sure.
So I guess what you're showing here is the instructions being executed by the GPU, but I'd imagine that in any real application, there's probably also, an Intel core where the main application runs and then it farms out stuff to the GPU, correct?
So, so the way it works is basically there is some CPU which at a high level basically sends a request to the GPU, which like the accelerator, which says basically here's a pointer to and there's an API which basically says execute this sort of frame, if you will. So we call it a draw call. It's basically a frame. The GPU then essentially just goes and fetches all the instructions. It is then basically completely autonomous and basically fetching all the instructions, all the data, everything that's required to finally produce the image, if you will. And then the signal completion to the CPU that says, okay, this frame is done. Does that make sense?
Yeah, and I guess I would imagine that in a lot of the applications you're talking about, more and more of the code execution can be offloaded to the GPU so that you're not actually doing a CPU to GPU and back transition, correct?
Right, so there are different kinds of applications. In a lot of graphics or like applications, you would just basically do most of the work on the GPU itself. And then there are lots of, I was just about to come to those in a few slides. There's what I call as a lot of heterogeneous applications where you want to do some processing on the CPU where the CPU is good at, and you want to do a bunch of processing on the GPU where the GPU is good at. And you heterogeneously operate on basically both of those together.
Thanks.
Okay. So for people familiar with CPU, this will look somewhat like your CPU basically pipeline. You're basically fetching an instruction, you're running it through your execution units you use. There are some registers. So we have registers here as well, along with shared memory. It's an extended register file. And then your load store unit. The big difference being that instead of a few threads or a few core, we have several thousands of threads running in parallel. Okay. So I'm going to basically try and explain what CUDA is so that it'll be easier to try and map what I've been trying to talk about into how it looks from a programmer standpoint. Right? So CUDA is basically, think of CUDA as is a way, just like in C on the CPU, you have a single thread, and you ask the thread to basically do some processing for you. Right?
Lacky, question?
Yeah, go ahead.
This may be basic, but what does CUDA stand for?
CUDA stands for, let me find out actually, I forgot what it stands for. Hold on one second.
Oh, we can look it up in Google, thanks.
You can look it up, it's C for whatever, somebody came up with this highly complicated name, which I never remember. I essentially remember it as C for graphics. That's why we call CG, and then that's what its original name, and then it evolved into what is called CUDA. Okay. So there's basically okay.
Somebody has kindly responded saying it stands for Compute Unified Device Architecture. So
okay. Yeah. So the way I would interpret that, or that very complicated sort of acronym, is it's basically an architecture to essentially take C with some extensions and run it on the GPU. And I'll walk through how that essentially looks like, in just this slide and the next. Okay. So in typical CPU applications, you have a single thread that runs, right? On the GPU, when we run, we basically don't run one thread, but we basically run n threads that are running in parallel. We call that a thread block. And then, this thread block basically has what we'll call barriers, where all the threads in the thread block will sort of wait for each other to make sure they reach that point before they continue making forward progress. And then what you basically send to the GPU is what we call a grid. The grid consists of a lot of thread blocks, and the thread blocks consist of a lot of thread. To make it easier to see, is think of a thread. A thread is something that basically has its own per thread local memory on which it is always operating. Threads communicate with all other thread blocks through some per block shared memory. So basically all these threads can basically communicate with each other through the shared memory, which is really, really fast. It's just like an extension of the register file. And then various thread blocks communicate to each other to what we call this global memory. This is the main memory. And so if I can take an example of an application, let's say like a separable convolution. So each thread would read the source data from the global memory and would perform a horizontal convolution. And then it'll write the intermediate results in the shared memory block. Okay. And the threads would all perform a local barrier to make sure all of the threads are done with a horizontal convolution. And then the threads will basically all then go and execute a vertical convolution on the data that was written out. And then we'll basically write the results of that vertical convolution into main memory, and that's how it would share with all of the thread blocks. So you finally get your entire convolution done. And to make it more clear, also let me go through an exact sort of source code, which will explain how basically this works. So in this particular case, the one on the top is basically the serial C code that will execute on the CPU. SAXP everybody is familiar with. You're just basically taking a huge array and basically you do AX plus Y on every element on the array. Right. So how would you execute this in using CUDA? So let's just take this example here where I have a really big array that I want to basically run in parallel on the CUDA. And just think of that basically every thread block that I showed in the previous picture, I want that to have basically 256 threads in that. Okay. The maximum size of a thread block can be up to 1K threads. So let's just say I want basically every thread block to have 256 threads. So I'll basically call SAXP with the size of each thread block is 256. So the number of blocks is basically my total size, sort of essentially divided by 256, right? And adding 255 more just to make sure if there's any left over, there'll be one more block. Okay. So this is essentially my total number of blocks, which is so the n essentially divided by 256, the ceiling of that. So in this code that essentially runs on the GPU, you see every thread needs to know what element of the array it belongs to. Right? So every thread is launched with a thread ID and its block index. Block dimension is essentially 256. It is this 256 value that it's given in. So every thread, by essentially doing block ID times x, so if the very first block, let's just say block t.x is 0 because the very first block, so x is 0. Dimension is 256, and it will get its thread ID. So the very first block, all the threads will have values. Essentially, I will be going from 0 to 255. The one with block ID of basically 1, where block ID has the next block, will be from 256 to 511, and so on. So every thread that's running will have its own unique I, and it will be performing this operation. So all of these threads will essentially be running in parallel on those green CUDA cores that I mentioned earlier. And that's how we get all this massive parallelism on the GPU.
Lacky?
Yeah?
3 questions. First question, who generates this code? Is this done by the programmer or does the system generate this?
So this code is basically done by the programmer. This is the app developer, just like the SAXP is essentially written by the app developer. So this is basically converting essentially the serial code into the parallel code. So think of it as basically pragmas that you add to make things parallel. This is the equivalent of how you write your code to make it run under CUDA. It is also true that basically Nvidia in general provides a lot of libraries that you can just basically link against, and it will provide various basically math libraries, various matrix multiplication libraries, various convolution libraries and stuff that people can directly use in their code.
Okay, thanks. Next question: the 256, is that the number of cores on this particular GPU, or will that number change as the number of cores rises?
The 256, it does. The number of cores on this GPU is sort of way higher. The 256 is basically essentially a number that people should use for how many threads that they need to be running together, so that there is local communication that's required across the thread. In this particular case, there is no local communication, so you could have even run with a smaller or larger size. At the end of the day, generate the same number of basically essential threads. It's just an example in this case.
And the third question: is there any difference between CPU threads and GPU threads?
Yeah, there are a lot of basically differences, right? If I can show this picture. So the thing to note is basically the GPU threads, when you're running the thread block, all of these GPU threads are essentially running the same program. Okay, there's one instruction fetch unit which basically is, per CUDA core, that's basically essentially then is running all threads and there is running essentially the same program. That doesn't mean that every thread has to operate on exactly the same way. It's perfectly okay to have divergence in the sense that an if statement and some threads do some work, other threads do some other work. But the way that works is basically, while if you have an if statement and the threads diverge, then only one side of that if statement is executing at a given instance till you reach a barrier, and we go execute the other side of essentially the else till you reach the same barrier. So the threads can essentially do whatever work you want, but to get maximum benefit and overlap, you want the threads to diverge as less as possible.
Lacky, I have another question. Is there an assumption that all the X of I and Y of I are all moved into local memory?
No, there is no assumption that all of X and I or Y of I are moved into local memory. You can fetch all of them directly from global memory. In this particular case, that's exactly what is happening.
Okay, so that means there'd be a lot of traffic going back and forth, right? Because you're even storing the value back.
Correct. This is an illustrative example in which case you're fetching everything from global memory and writing it back to global memory. Note that our memory bandwidth is also extremely high. So we're essentially built for streaming and hiding all the latency. So because we have so many threads, hiding all the latency to global memory is essentially what is essentially the GPUs are extremely good at. You get a lot of benefit in terms of even performance acceleration more if there is something that you can share across threads in a thread block within basically what I'll call the shared memory. And then on a per thread basis, you also have some scratch, what I would call is basically local memory, where you have your stack per thread that you can use as well.
Thank you.
Okay. So, can folks see this on the screen? So this is just an example of using CUDA to basically, essentially simulate rigid bodies. You can basically see that we can, we can basically model rigid bodies extremely well now, and model all the physics and stuff using basically, using this accelerator that we have. These are libraries that we provide that basically people can use to essentially model fluid, rigid bodies, all kinds of things that we have. Okay. Here's another example of fur, modeling of fur. You can basically see how all of that essentially, again, through CUDA, we provide all of these libraries that will do essentially all of that. This is just an example of, so all pretty pictures, but this is extremely important and extremely key for basically not only for high performance computing, but and games and various other applications that we can go
Yeah,
Okay.
I mean, Lacky, this may be obvious to you guys because you're in the graphic space, but with and without pictures would be a lot more effective in because the texturing and the lighting, it takes an enormous amount of computing to actually make it look right, even though.
That's correct. Exactly. Right. It is very, very hard to get this look real and get this look right. It takes massive years of work and innovation and to get all of this actually look right. As I said earlier, lighting is the most important piece. Texturing is also very, very critical. It's extremely, you get the right sort of filtering and stuff. But getting lighting right, and that also depends, a lot of lighting is done using texturing and shadows and stuff. That's where, there's still a lot of ways to go before we get to something very, very close to being real. So if you look at human skin, for example, getting lighting right in there, that's still not a solved problem.
And is that problem pretty much an algorithm problem, or it's sort of what's the gating factor there in making it more and more realistic? Is it computing? Is it just sort of mathematical modeling?
It's basically a lot of computing. You can. It's not basically an algorithm question. It's basically the level of detail that you need to model it. So inside the skin, there's a lot of basically substructure. There's a lot of reflection, refraction, and stuff that happens within the skin. So you have to model all of that accurately and correctly. So it's mostly basically computational horsepower that you need to get there to do it in real time.
A quick question, Lacky. I don't know how you're doing for time, but the questioner asks, can you talk a little bit about the power consumption in GPUs versus CPUs?
Sure. I'm going to come to that in a second. If you can just wait for a few minutes, let me just walk through the next 3 slides, and then I believe I would have answered that question. Okay.
Okay.
So again, I mentioned the thing at the beginning. So let me just walk through a few of the places where GPUs are really, really used, and so people get a sense of what it is. And power is one of the key parts of this as well. So the number one place, right? We're used very widely in gaming. We have, as I said, a lot of gamers. People love to use the Nvidia GPUs for playing games. And there are lots of basically innovative things in there to not only make things look real, but to also play with other people, to do something very special. But there's a lot of stuff, cool new thing that we make sure we're also working with the display vendors to make sure your display is highly synchronized with how the GPU works. So there are all kinds of those things that we've added inside the GPU. Okay. The next one is basically auto. So we have like 80% of people who have workstations that basically do design use the GPUs. Right. Pretty much across the world, whenever people think of basically trying to do modeling of real stuff, they essentially use the Nvidia GPUs. And so the thing I want to also mention is that every film nominated for Best Visual Effects since 2009, the effects have been created on Nvidia's GPUs. So you can see how critical it is for essentially creating these effects. So what I was trying to get to the power efficiency is this, right? So pretty much all of 85% of the accelerated HPC or supercomputers of the world are basically accelerated using GPUs today. In terms of, when I say 85%, I don't mean systems, but I mean basically if you just look at the throughput that you get from them, that throughput comes from the GPUs. And essentially of the top 15 most energy efficient supercomputers, all of them are on GPUs. So the power efficiency, right, of the GPU is because unlike the CPUs, which is operating every thread independently, we focus a lot on basically sharing as much stuff as possible across many threads together. As a result, we are doing way less work on a per thread basis compared to what you do with the CPU. because we are amortizing the cost of the single fetch across, let's say, 32 threads instead of one thread. Sorry, is there a question?
Go ahead.
I couldn't hear that, so I'll keep going. So energy efficient is basically really paramount to making supercomputing actually advanced, because they're all essentially limited by the power they can deliver to the supercomputers right now. So the Summit system at Oak Ridge National Laboratory, which is basically being sort of built and trying to be completed, it's capable of delivering 150 to 300 petaflops, right? And then basically, this would not have been possible essentially without using GPUs. If they just use CPUs in the power budget they had, they would essentially be about close to 10 petaflops. So it's about a 15x improvement in power efficiency by making sure they can use GPUs to power all of these the supercomputers. I don't have a lot of time left. I'm going to accelerate through a few slides now. Sridhar, you asked about basically how the CPUs and GPUs coexist. There's a lot of applications where you require heterogeneous computing. So you need to cooperate between the CPU and the GPU. So most of the things that run on the GPU, you can think of it as separated into two groups. There is simulation and then there is visualization. Right. And so we get a lot of about 10x or more speed ups for really, really big applications. So a lot of people use GPUs in medical imaging, where instead of basically using the CT scanner, which basically has a lot of cancer risk and stuff, they now use basically GPUs to reconstruct the images. So it takes about 30 times less radiation than it used to take before. Seismic imaging, this is basically oil and gas stuff. The amount of time it takes them to discover if the oil exists or not is basically reduced by 10x. So pretty much every single oil and gas customer company now uses GPUs to do a lot of essentially their computation. Okay, I'm going to skip through that and talk about machine learning because people are really interested in this. So, okay, here's the ImageNet is a challenge produced by DARPA, and AlexNet is also one of these sort of benchmarks people use on the in the machine learning field. This is basically, you have essentially presented an image, and you need the system to tell you what this image is. So you use lots and lots of images to basically first train your network, and then you can present stuff to basically identify what that image is. So I'm not sure how many of you guys have gone to Google Photos recently, but if you go to Google Photos and you basically, this is what they announced a few weeks back, and if you have a bunch of photos, they will actually identify that it's the same person over the last basically 15 years, right? As people age and stuff, they can classify and identify it is the same person. You can figure out where you have been in the photo by looking at the picture without you having to actually explicitly tag it. And they're doing all of that using the GPUs because they've trained their network to basically fully understand and recognize all these images. Right? So you can see basically essentially how fast essentially the GPU is compared to basically a CPU for doing essentially training this wide number of millions of images that you need to train it with, that you can then basically within more than 90%, I think it's close to 95% now accuracy, identify an image that's shown to you. So all of this essentially works through these CUDA, CUDA, these are libraries that we provide that basically uses CUDA to basically essentially accelerate the training and the inference of these images.
Lacky, a quick question here.
Sure.
How does streaming video work in relation to GPU the parameters of the image are sent standards such as MP4, etc.
Sorry, can you repeat? I did not understand the question.
Yeah, the questioner asks, how does streaming video work in relationship to GPUs? The parameters of the image are set by standards such as MP4, etc.
Okay. So the streaming of images, that's basically those are MP4, H.264, H.265. Those are all basically things that are encoded, decoded, and stuff, right? So those are images that are essentially just sent out. What I'm talking about here is basically recognizing of an image as to what's inside that image. So right. So you take the image, you will essentially break it down into pixels that you have, and then once you've broken it down essentially into pixels, you find appropriately the edges and stuff, and you use all of that information, feed it into a neural network, if you will. That's essentially the deep learning network with different layers, and it will basically should identify what that image was. Right? So that is completely orthogonal to essentially the standard and stuff that's there in the streaming. Does that make sense?
Yeah, if that didn't answer the question, can you follow up, please? And otherwise, Lacky, please continue since we are limited on time.
Sure. Okay. So the other part of basically where the GPUs are getting used, in addition to basically a lot of cloud services for machine learning, is now in the mobile side, right? So I'm going to talk on the mobile side, right, a little bit about basically, having, as I mentioned, tablets and game consoles and stuff that we have, but I want to spend a little bit more time on basically the automotive side. Right? So on the automotive side, basically, we have a lot of cars basically now use Nvidia GPUs in their infotainment systems and basically the driver assistance system. So if you look at the automotive application, right, so we sell these basically DrivePX, these essential modules to the auto guys to actually put it into the cars, and then that basically helps basically do a lot of driver assistance, self-driving cars and stuff. So the key in this picture is basically to know that inside the automotive, what's required, this DNN, is just like the machine learning framework, right? When you're doing a self-driving car, what you need to know is what are the objects you're seeing. It's basically an image recognition stuff. It's a computer vision problem, right? You need to know what is it that is on the road. Is it a small pebble? Is it a big rock? Is it a car? Is it a bicycle? Is it a sign? What is it that you need to recognize? And so deep learning is essentially what all the automakers are essentially using to basically create self-driving cars. Right. And so, so GPUs are basically, since we're extremely fast and efficient, both from a power standpoint as well as efficiency standpoint, to be able to solve these problems, almost all the automakers are using this to basically put into their self-driving systems. Here's an example of actually a working system. Right, we have this in-house where you can drive down. This is a road actually in San Jose. Can drive down and then basically, this is what it will show up on your dashboard. One last thing, I know Sridhar and a few others may be interested in this because we worked at OmniShift together. There's a lot of stuff that's basically going into the cloud now. So Nvidia works with a lot of virtualization systems, and to basically make sure that basically people for employees who want to basically bring your own device to work, we have servers that basically people can use to stream essentially the screen to them. And the big difference between a Citrix-like system that does that, whereas we work very closely with Citrix, and the GPU's big system is the systems that we build actually accelerate the creation of the screen through the GPUs, right? So we want to basically make sure that these are high-end applications like Pro-E, like SolidWorks, like CUDA, that can all essentially be rendered from a server to multiple workstations or multiple screens at a time, right? And so NVIDIA also provides essentially these things that can then be housed into the cloud, whether it's the enterprise cloud or it's basically the cloud into like an Amazon cloud that you can then basically send stuff across any devices that you want. Okay. So we have basically a lot of accelerated virtual desktops. I want to basically quickly talk about this slide, which is basically critical in terms of how we can make sure we can even stream stuff across servers to somebody's client, right? If you look at the most important thing while you're playing a game or you are doing work on your workstation, right? If you click a mouse and if the lag is really, really long, then it won't feel responsive, and you will feel that it's not, the system's not acting as you expect it to be. Right? So the thing that we have solved, which nobody else has done yet, is basically reduce the latency in the system from what we have in the cloud to the person's client at home. Is this latency by which when they click to actually go to the server, get the image rendered and back. And we've accelerated that so that it basically is as close to somebody playing a console game at home. So that is why it allows us to basically essentially serve stuff up from the cloud. Obviously, your server cannot be really, really far away, like in India, and expect to run it in San Jose and expect it to work. But as long as that latency is manageable in terms of basically milliseconds to access stuff, we should basically be good. Okay. Or basically, as I mentioned, I want to spend some time basically on NVLink, which is the thing that we haven't actually seen in any GPUs so far. This is the last part of my presentation. A lot of people have always basically criticized GPUs as basically, hey, GPUs, you guys have a huge processing power, you guys have huge memory bandwidth, but you always need to be connected to the CPU. I think, Sridhar, you asked this question, somebody else did as well. And you need to move data from the CPU, so you're always limited by this PCIe link, which is your bottleneck. Right? And as long as you have to move data from the DRAM to the GPU's memory and operate on it really fast, but if this link is really slow, then how are you ever going to basically be able to accelerate things? So what we have done is basically, we have replaced that PCIe link with our own custom link now that basically increases the bandwidth between the CPU and GPU by more than 10 to 20x, so that basically we can transfer data from the memory into the GPU's memory extremely fast and then operate on it at super high speeds. And so by eliminating this as basically being the bottleneck. And so we can also take that and basically scale that up, run it across multiple GPUs. So now you can basically have a single CPU connected to basically multiple GPUs, and the GPUs can connect to each other as well and basically share stuff between them. So this is how we basically scale stuff in the servers and can access basically improve basically the footprint of the GPUs for a single CPU. We can take that even further, as I said, and can keep scaling this till now. Basically, we have systems up to 16 to 32 GPUs together. Right. And so, what is an NVLink? It's basically essentially, it's a differential connection. It's a bidirectional link, basically with an extremely low power, 10 picojoules per bit transferred, and it's basically something that's custom that we've built. That is pretty much one of the most efficient interconnects that's there in the industry right now. Okay. So that's the NVLink, and so I just want to make sure I get done in time. So I have 2 or 3 minutes if there are any questions at the end.
Okay, folks. So please,
Lacky, how far?
Go ahead.
Sorry, when you say NVLink, how far are we talking about? Is it has to be on the same backplane, or is it?
Think about basically up to 1 or 2 feet.
Okay.
Folks, while you're thinking about the questions, I have a couple here that have come in via chat. The questioner asks, what makes the GPU so much more power efficient than a CPU?
Yeah, the GPU is a lot more power efficient than a CPU for the kinds of applications that the GPU can accelerate. Right? If you run a serial thread where you have just one thread that is active and running, then it's not going to be power efficient than the CPU. Right? Then you're basically wasting a lot of the stuff on the GPU, which is essentially sitting idle and burning, essentially at least wasting the leakage power, if not the dynamic power.
Okay. Next question: will apps have to be rewritten substantially to exploit new GPU architectures, whether they have more cores or more threads per core?
No. So we basically through CUDA we provide basically essentially a layer of translation, if you will, among intermediate called PTX. So apps don't need to be rewritten. We basically always change the layer from PTX down to our hardware, and that's something that it's always invisible to the apps. So we as long as the apps are, there are some ninja guys who will develop and tailor the apps to work in exactly the right number of cores. Yeah, sure, they will, they will have to rewrite it, but as long as people are basically using what we traditionally provide, the big advantage of the GPU is that when we change from a single core to thousands of cores, the apps don't have to change. So the same application runs on a handheld phone, that same application runs on a supercomputer without having to touch the code.
Okay, folks, I know it's pretty much 1 o'clock, so I guess Lacky, thanks for a great webinar. Lacky's coordinates are either on the slide, or you can please send me questions. I can follow up with Lacky and connect you guys if you need to. And I guess our common practice here, Lacky, as in our previous webinars, is a custom, I think suggested by Max Lansker, who's here today, is to actually give the speaker a virtual clap, since we're all across the globe from 2 or 3 countries, China, India, etc. So I guess why don't all of us unmute ourselves? I've unmuted everybody here, and let's extend Lacky a warm virtual applause for an excellent talk and informative talk. So let's go ahead and do that right now. So thank you, Lacky. I guess let's see, with that, it's a wrap. What we'll do is next webinar is on September 18th, when Soham Das from University of Florida is a PhD candidate. He's going to talk about network topology optimization in data center networks. And I'm still working with a speaker for the August slot. If so, please stay tuned for that reminder. Seminar for this webinar, the surveys for this webinar will go out shortly, so please fill that out. That always helps us improve our offering, whether you have comments about our technology or the way this was moderated, etc. Please send us your feedback, both positive and negative. With that, thank you very much for attending this. We'll see you all.
Hey, thanks a lot, guys. Thank you. Okay, bye.